Take a look at this yellow Strandbeest model. When it moves, it looks almost biological, but there are no motors or computers inside. Every step it takes is driven entirely by simple, circular geometry. This visualization shows exactly how that works. We can map the physical plastic parts directly onto a mathematical framework to see the strict rules controlling its stride. If we strip away the plastic, we're left with the bare skeleton. The entire system relies on just two anchor points, point C and point F. These are bolted to the background. They cannot move. Then there is point P. Think of P as the engine. It travels in a continuous, perfect circle around point C. That single, repetitive rotation is the only input in the whole system. The tumbling, walking motion of the leg is strictly a mechanical reaction to point P spinning in place. So how do we build the rest of the leg from that circular input? Let's figure out exactly where joint D needs to go. We know it has to connect to the moving point P and to the fixed point F. In a mechanical linkage, a rigid rod attached to a pivot point can only do one thing. It sweeps out a perfect circle in space. We know the exact length of the connecting rod from P. If we sweep that length outward, we get a blue circle. Joint D has to lie somewhere on this line. But joint D also connects to point F by a second rod. We sweep that length out from F, giving us a red circle. There is only one place joint D can physically exist, the exact intersection of those two circles. Once we lock the joint in, we clear the circles away so the diagram stays readable. Let's test that logic. The lower push rod extending from P is 5.1 units long. The connecting bar from F is 3.2 units long. Where do we draw the circles to locate joint E? We anchor one circle at P and the second at F. Where they cross, we drop joint E, and then we wipe the board clean. Whenever you have an unknown joint connecting two parts in a planar mechanism, its exact spatial coordinates are always solved by finding where those two radial paths cross. This diagram shows the complete structure, highlighting the final major components. Notice the two large shapes, the red upper triangle, DFG, and the green lower triangle, EHQ. Look at the color coding on the connectors. The purple bars act as stabilizing bridges, while the blue rods are the drivers, pushing and pulling the structure. These colored triangles are entirely solid. They do not warp or bend. All the flexibility in the leg comes exclusively from the circular hinge joints connecting them together. The engine spins, the blue rods push against the rigid triangles, and the purple bars keep everything aligned. That chain reaction turns a basic circle into a coordinated step. This visualization shows the final output. Point Q traces a thick, red, D-shaped curve, acting as the machine's foot. Notice the bottom edge of that red trajectory loop is completely flat. That horizontal line provides level ground contact, allowing the machine to glide smoothly. This interface shows the exact measurements that make that flat step possible. The parameter sliders on the left dictate the specific length of every rod and bar in the leg. If a single piece is manufactured incorrectly during assembly, the geometry breaks. Let's see what happens if we shorten the upper crank arm by just a few millimeters. The swept circles used to find joint D shrink. They no longer overlap, leaving empty space where the connection needs to be. Without that intersection, the math cannot resolve. In the physical world, the leg binds, locks in place, and the mechanism snaps. The system rests on a strict chain of command. Fixed points anchor it. Rotary input drives push rods, and push rods maneuver the rigid triangles. The final walking motion looks graceful and complex to the naked eye. But underneath, every single movement is completely constrained by the precise logic of intersecting circles.